We're tackling straight lines today. It's pretty basic, right? But trust me, there's a surprising amount of depth here. We're going to unearth those hidden gems and see how they connect to the bigger picture.
Well, they are fundamental. What makes straight lines so fascinating is that they're simple enough to grasp intuitively, yet they underpin so much in math, even in how we understand the world.
We're talking about straight lines on a 2D plane, basically. A flat surface that extends infinitely in all directions like a giant piece of graph paper.
A classic coordinate plane.
And the beauty of a 2D plane is that we can pinpoint any location on it using coordinates.
And the math map does a great job of illustrating the different coordinate systems we can use. Rectangular, polar, even complex coordinates.
It's like having different languages to describe the same location, each offering a unique perspective.
I like that analogy. So you're probably familiar with a rectangular system, where we use XY coordinates to pinpoint a point's location based on its horizontal and vertical distances from the origin.
Like a grid.
But we can also use polar coordinates, which describe a point's location based on its distance from the origin and the angle from a fixed direction.
Okay, so it's like saying walk 5 steps at an angle of 30 degrees instead of walk 4 steps east and 3 steps north.
Precisely. And then there are complex coordinates, which use those imaginary numbers to represent points on the plane. For example, if we take the point 3, 4 in rectangular coordinates, the math map shows us this can also be expressed as 5, 53.13 degrees in polar coordinates, or as 3 plus 4i in complex form.
It's amazing how a single point can be represented in so many ways.
It is. And the choice of which coordinate system to use often depends on the problem you're trying to solve. Each system has its strengths and helps us see the problem from a different angle.
Okay, so we've got our 2D playground all set up, and now it's time to bring in the players. Straight lines. Now, we all know a straight line when we see one, but what actually defines a straight line mathematically?
Good question. Our sources emphasize two key characteristics. First, a straight line is determined by any two distinct points on that line. Give me 2 points, any 2 points, and I can draw one unique line that passes through them.
It's like connecting the dots.
Second, we can represent a straight line using an equation, a kind of mathematical code that captures all the points residing on that line.
And speaking of equations, our sources lay out 3 main forms: slope-intercept, point slope, and standard form. Don't worry, we won't get bogged down in the formulas right now, but the key takeaway is that each form gives us a different way to express the same line, highlighting different aspects of its behavior.
It's like having different tools in your toolbox. You choose the right tool depending on the job.
Love that analogy. Now, straightlines.pdf has this really cool visual, an image of a flamingo.
A flamingo.
Yeah. And when you look at the flamingo's body, it almost perfectly forms a cross, showcasing 2 intersecting straight lines right there in nature.
I see what you mean. And what's fascinating is that the author of A Contribution to the Conversation connects this image of intersecting lines to the Christian cross, drawing on a passage from Proverbs. They suggest it's like how in life, interactions with others can refine and shape us, just as iron sharpens iron.
It's amazing how even a simple geometric shape can hold such profound meaning. But let's get back to the lines themselves. One of the most important concepts to understand is the idea of slope.
Slope is often denoted by the letter M, and it essentially tells us how steep a line is.
And more importantly, the slope reveals whether a line is rising, falling, or staying perfectly horizontal.
A positive slope means the line is rising from left to right, while a negative slope means it's falling. A slope of 0, and we've got ourselves a horizontal line flat as a pancake.
And of course, we can't forget about those vertical lines, those straight up and down lines.
Those are interesting because their slope is considered undefined. They represent a situation where the line is so steep, its incline is impossible to quantify.
Kind of like those classic optical illusions where you have 2 lines of the same length, but one looks way longer because of the direction it's pointing.
Exactly. Our brains are naturally tuned into those slopes and angles. But getting back to slope, it's not just about describing a single line in isolation. It's also incredibly useful for understanding the relationships between lines.
You mean like parallel lines and perpendicular lines? Those always kind of tripped me up back in school.
Well, imagine parallel lines as 2 cars driving side by side on a perfectly straight highway. They're traveling in the same direction, maintaining that same distance from each other. That's because they have the same slope.
So if one car veers off course, changes its slope, they're no longer parallel.
Precisely. Parallel lines are all about consistency, that constant, unchanging relationship. But perpendicular lines, on the other hand, are a bit more dramatic.
Yeah, perpendicular lines are like those intersections where roads meet at a perfect right angle.
And their slopes have a very specific relationship.
But how do we actually calculate slope in the first place? We're basically figuring out how much the line rises or falls vertically for every unit of horizontal movement.
It pops up in all sorts of applications, from physics to finance, whenever we need to quantify rates of change.
Speaking of real-world applications, straight lines, linear graphs,
Hmm.
Parallel has that interesting example with the ship navigating its course. Can we delve into that for a sec?
Absolutely. In this scenario, we have a ship sailing north at twice the speed it's heading east.
So for every 2 units it travels north, it travels 1 unit east.
Precisely. We can actually visualize this as a right triangle, where the ship's northward movement is the vertical leg, its eastward movement is the horizontal leg, and its actual path forms the hypotenuse.
Eh.
This example gives us a tangible sense of direction and even speed in this case.
Now, I'm curious about how straight lines connect to the world of functions. Those always seemed a bit more abstract to me.
Well, our sources do a good job of clarifying this relationship. Not all lines represent functions, but all linear functions can be represented by straight lines.
Okay, so let's break that down. The math map reminds us that a function is essentially a rule that assigns each input value to one and only one output value. It's like a vending machine. You press a button, input, and you get a specific snack, output.
That's a great analogy. And to determine if a graph represents a function, we use something called the vertical line test.
I vaguely remember this one. It's like sliding a ruler across the graph, right?
Exactly. If any vertical line you draw intersects the graph at more than one point, then that graph does not represent a function. But if every vertical line intersects the graph at most once, then congratulations, you have yourself a function.
And then since most straight lines pass this vertical line test with flying colors, they usually represent functions, the exception being vertical lines themselves, right?
You got it. Vertical lines are the rebels of the straight line world when it comes to functions. They fail the vertical line test miserably because a single x value corresponds to infinitely many y values.
Okay, that makes sense. It wouldn't be a true function if pressing one button on our vending machine gave us every snack at once.
Precisely. Now, just as we have functions, we also have their counterparts. Inverse functions.
Right, inverse functions. They're like hitting the undo button, reversing the action of the original function.
A perfect analogy. If a function takes you from point A to point B, its inverse function brings you right back from B to A. We see examples of this in our sources with linear equations.
And the math map walks us through the process of actually finding the inverse of a linear function, which involves a bit of algebraic manipulation, but it's ultimately pretty straightforward.
It is. And just as the vertical line test helps us identify functions, we have the horizontal line test to check for inverse functions.
So if a horizontal line intersects the graph more than once, that function doesn't have an inverse.
You've got it. Now, remember that image of the flamingo we talked about earlier?
Yeah, the one forming a cross with its body.
Exactly. The author makes this fascinating connection between the flamingo's flocking behavior living together on a 2D plane and the interconnectedness of individuals in a community.
That's a unique parallel. How so?
They suggest it's like each person represents a point on this plane, and their relationships with others are like lines connecting them. Just as a plane contains infinitely many points, a community is made up of countless individuals, each with their own unique position, but connected through shared experiences and bonds.
It's like we're all navigating this giant graph of life, forming connections and influencing each other's trajectories.
Exactly. And just as we can analyze the relationships between points and lines on a plane, we can use those same mathematical concepts to study social networks, economic systems, even the spread of ideas and information. So we can't wrap up our deep dive into straight lines without talking about vectors.
They add a whole new dimension to our understanding of lines.
Think of vectors as arrows on our 2D plane. They have both magnitude, which represents their length or size, and direction, indicated by where that arrow is pointing.
And what's cool is that our sources show us vectors can be represented both graphically, using those arrows, and mathematically using components.
For example, on page 8 of Straight Lines Extending to Vectors, we see the vector u represented by the components, 3, 4. This tells us that the vector travels 3 units horizontally and 4 units vertically.
It's like following directions on a map. Go 3 blocks east and 4 blocks north, and you'll have traced out the path of that vector.
Precisely. And just like we can add and subtract numbers, we can add and subtract vectors.
So if we have one vector pointing east and another pointing north, adding them together would give us a new vector pointing somewhere northeast.
You got it. It's like combining forces. Each vector contributes its own push or pull, resulting in a new vector that represents their combined effect. And we can even scale vectors, making them longer or shorter by multiplying them by a scalar.
It's like adjusting the volume on a sound wave or the brightness of a light.
And these vector operations aren't just mathematical curiosities. They have countless applications in fields like physics, engineering, computer graphics, you name it.
It's amazing to think that those simple straight lines we started with have led us to this incredibly rich and complex world of vectors and their applications. So, as we wrap up our deep dive into the world of straight lines, what are some key takeaways you hope our listeners will walk away with? How does this deep dive into straight lines connect to other areas of knowledge, other areas of inquiry?
I think it highlights how mathematics isn't just a subject confined to textbooks and classrooms, but a language that helps us decipher the world around us, from the movement of planets to the behavior of markets to the very structure of our social connections. To our listeners, I encourage you to continue your own deep dives, embrace that curiosity, and never stop questioning and exploring the world around you. Who knows what fascinating insights are waiting to be uncovered?
And on that note, we'll wrap up this deep dive into the world of straight lines. Until next time, keep those minds curious and those questions coming.